Metrology Day. So, metrology. It's not on the right screen. Now, metrology. There we go. Remember, metrology is of the five big ideas. Metrology, or measurement, is the one that ties everything together, because we have to be measuring things at all points in the process. So it's really important to do metrology, to understand metrology. And we will do some metrology now. We'll understand it more as we move along through the quarter. So, from the videos, why does metrology matter? Yeah.
It's what lets us communicate about like science and other things that are quantity dependent.
Okay, so it helps us to be able to communicate well for quantity dependent items.
Like the study of metrology allows us to have organizations that standardize our measurements, so we're using the same measurements.
Okay, that seems pretty helpful and pretty important. Yeah.
So that globally we all understand what we're talking about in terms of like anything that's quantifiable.
Okay, that's good. And on a much more personal basis, you want to get what you pay for. So if you go to the store and you buy a gallon of milk, you would like it to be a gallon. You would like to not get 0.7 gallons because somebody else had a different idea of what that was. So on any of those things, whenever we're buying or selling, we need to have metrology to be able to measure what we are exchanging. Yeah, so you talked a little bit about this. How does metrology work so that people all over the place can understand that they're getting the same measurements? For anybody, what's the method? Yeah.
There are different organizations that institute specifically what things are. There's the one in French that has different weights and measures. One, International Bureau of Weights and Measurements.
Yes, the IBPM.
Yes.
Yes, and every country has one. They have the oddest conference when all of those countries' institutes get together. It is the International Conference of National Standards Institutes Committees. And so to have international and national in the same title seems very confusing, but anyway. The people who tend to work at those organizations are an interesting lot of people. At one of the organizations, well, let's see. Later on, we'll see something about the watt balance. And so I went 20-ish years ago and visited where they were working on the watt balance. And at that point in time, the person who was there worked out in a building by themselves out in the middle of this nice campus that they have for the National Institute of Standards and Technology in Gaithersburg, Maryland. Person worked in this little building by themselves. They had been working at that point 20 years to find the 14th decimal place of Heisenberg's constant. And that work culminated in 2018, which would have been, I don't know, about 17 years later. So it was like 37 years of work for that person to learn the 14th decimal place of a constant to a good enough understanding that they could then say, yes, we now know what a kilogram is. So it's an interesting breed of people. In the video, the guy who runs the Moore 48 CMM that you saw is probably one of the most normal people there. I mean, the best adjusted, the most personable. And in that, he's still kind of an odd duck. I mean, these people who are finding every little tiny error source and quantifying it and working to reduce it is pretty amazing. So anyway, what were some of the things that they had to do on that coordinate measuring machine to reduce error and uncertainty?
Under one of the machines, they had to have air pads
Yep.
underneath it to keep it from vibrating when the rest of the floor vibrated.
Yeah, and the thing that they didn't talk about was it's on air pads on a concrete floor. That concrete floor is a separate block of concrete from the rest of the building. So they dug a deep pit, they filled it full of concrete. Generally, I don't know how deep theirs is. The place that I last worked, the concrete slab was 12 feet of concrete, just a huge block of concrete. It is physically separated from everything else, and that block of concrete is also on foam squishy things to separate it from the earth. Even so, at the one in Maryland, they have to accommodate the tides. The ocean is 20 miles from Gaithersburg, and the tides adjust the lift of the land with respect to the water table. It's nuts. Yes, Adrian.
They also have to put it underground. They put compensate for the temperature and everything in the area around it, and the humidity in the air and everything.
Okay, so you have to compensate for the air, temperature, and humidity. And it was underground. What were some of the ways that they compensated for temperature and humidity?
I think they said they turned the lights off.
Yeah. So when I was there 20 years ago, they ran it. At that time, there weren't LEDs all over, so fluorescents were about the least heat-producing light source that you could have. And it had fluorescent lights that all reflected off the ceiling so that there was no light directly on the table. But as they were measuring something, they would go measure the other end occasionally, or if it was small, they would still move the bridge away so it would not cast a shadow in one area for too long. And now they run it with the lights out. And I don't know if you noticed in there, it still had, probably not, but it still had the fluorescents hanging down. They weren't on, and it had little LED strips up on the ceiling. So already they're on a very low temperature light, but they're still running it with the lights off. Yeah.
They made sure that like if someone went in there, they had to like leave for like several hours before they turned the machine back on.
Yeah, he said it was ruined for the rest of the day because they were in there filming. Pretty crazy that one person walking through does that.
They also took into account any deviation that could ever possibly make it. Like, it's like, okay, we've seen that before, so we can just correct it so it's still along the line of deviation.
Okay, so you have to have a machine that has super repeatable motion. It doesn't have to be super accurate, we'll talk about this in a minute, but it has to be repeatable so that you know it's gonna deviate the same way every time, and then you can map it out of the machine. So as you go up in the expensive machine tools, they will do that. So ours do a small amount of deviation control, they do linear correction. But as you go up in cost, they get better and better and better at that. Anything else? Yeah.
It wasn't just that they were like climate controlling the room, they were also taking measurements and then adjusting. So, they climate controlled everything and, moved the electronics out and all that stuff. And then they also took measurements of temperature and humidity and all of the things that might be varied and accounted for any deviation from what it ought to have been.
Right.
Separately.
Yeah. So they had 3 probes on the table to know what it is, so you can compensate for the temperature. They also have to do that in the tubes. They said that that one has linear laser interferometers to measure the position of the axes, and the amount of carbon dioxide in the atmosphere affects them, as well as the humidity. Yeah. They'd taken that one cover off the machine because it got a little hot behind the cover, so they wanted more airflow behind it, so they took off the little more symbol. By the way, those machines and the highest precision machines in the United States outside of the semiconductor industry, so all of the rest of the precision machines in the US come from Keene, New Hampshire. It is a tiny town in New Hampshire. And what happened was somebody went to Keene and they started making high precision machines. And then they trained a bunch of other people how to make high precision machines. And so they went off and formed other companies that were not competing with the first company. So Moore was about the first company there. And then they formed these others, and some of them are pretty funny. One of them, this one guy started a company for diamond turning, so making super smooth optical surfaces. And he got bought out by a European company. And so he said, that's fine. It had a non-compete clause for a year. So he went somewhere else and developed new technology and then moved back to Keene and started another company right across the street making competing machines with his previous company. And he got bought out again. And so I don't think that he's resold the same company for a third time, but he at least did it twice, which seems, I mean, that's good work if you can get it. Anyway, interesting. Metrology means, metron means to measure, and logia means to speak or to study. So interestingly, the Greeks had this idea that you should study and understand something before you talk about it, which seems like something we could all learn. So that seems good. We're mostly going to be talking about dimensional metrology, which is the metrology of length. We'll look at some others just because they're fun. All of the metrology is pretty cool. But anyway, so we need to have a standard so that we're all measuring the same thing and measuring the same ways. Otherwise, we get into fish contests. So we need to understand, are we making the part correctly so that our customer knows that they're getting the correct part? We need to know, is there a dimension that we need to improve, something that we need to tighten up so that we don't scrap as many parts, but we can also understand, is there something where we're holding it to way too tight a tolerance so that we might be able to take that and put it on a machine that had lower tolerance capability and use our higher tolerance machine for a different process or a different part that required it. A while ago, it's quite a while now, Ted came to me and Ted said, hey, I need one of these to position some things on my satellite. And I said to Ted, great. And he said, can you make one of them? And I said, well, I don't have a way to measure it. And so I think I can make it to the tolerances that you're telling me, but I can't measure it. So I'll make you the one that's the best that I can. So $60,000 later, I gave him actually 5 of these. And he said, wow, that's cool. These are exactly what I wanted. Are they correct? I said, well, remember, I told you I couldn't measure them. And he said, how much would it cost to develop a system to measure them? I'm like, well, $35,000. So he gave me $35,000, and then we went off and developed a system to measure them. The reason it is so hard to measure is because these are little tiny portions of a sphere, and a little tiny portion of a sphere is super hard to measure because if it's supposed to be here and you measure it as being just a tiny bit different, that totally changed the diameter of the sphere and the position of the center point by a lot. A little tiny adjustment right here is a huge change for the center point and the radius of the sphere. So anyway, those were inflated prices because we had to support all our managers and all our equipment and everything. But it was an interesting time, and it was just important in that instance that I was up front with Ted and said, I don't have a way to measure this, so I will do the best that I can, but I cannot guarantee it. So anyway, if you need one of those, I used to have the equipment to be able to do it and the ability. I don't actually know what that satellite does. Ted was never able to talk about anything he did. So things that we have to know. We have to understand a lot of terminology, and so that's what we're going to talk about for a little bit here. Accuracy versus repeatability is the first thing and the most important concept, and it is misused a lot. The understanding of these two is misunderstood very, very often, or just people will misuse the terms. If you want people to make fun of you, go to a precision engineering conference and misuse these terms, and they will do so. So accuracy is the ability to have the average of your values, the mean of your values at the center of your target. So it means that it is described by the mean or the average, So if we were trying to hit a number, accuracy would mean that our average was right at the center of where we wanted it to be. The other term that we often hear is repeatability. So repeatability is the standard deviation. You can think of it as that. It isn't quite, but it's close enough. So am I able to do the same thing over and over and over and over? So if I make 100 parts, do I get the same value? And I want to crunch that deviation down. I want to have the smallest deviation that I can. So if I were shooting arrows at a target, if I were accurate and repeatable, all of the arrows would be right at the center, so very closely matched together. Because they're repeatable and accurate means that the average of them is right at the middle. If they are very close together but not quite at the center, they are repeatable, but they're not accurate. I can have them going all over the target, completely spread over the target, and as long as the mean of those is at the center, I'm okay for accuracy, if accuracy is my goal. And then this last case is something that is quasi-repeatable, but not long-term repeatable, and inaccurate. So maybe if I run 10 parts in the morning, they're all the same, but if I run 10 parts in the afternoon, they're closely grouped, but at a totally different place. Okay, so if I have a machine, and it's not right here, right now, it's not accurate and repeatable, what do you think I would prefer? Would I prefer an accurate machine that's not repeatable, or a repeatable machine that's not accurate? Yeah.
You don't want the flyers, you want to be able to move the entire group
Okay.
in one direction.
That's right. So I want a repeatable machine that's not accurate because I can change the parameters to change the accuracy. I can move it to the right location. I can alter my process some. But if I have a process that is not repeatable, if it's just spread all over the place, then I don't have much hope on that machine of being able to make better parts. Now there are things that we can do to reduce problems with repeatability. Any guess what the biggest source of a lack of repeatability is on a manufacturing process, generally?
User error.
The user, yeah. Darn people. The people are really hard to get them to do the same thing exactly the same way. And so what you need to do is design the process so that it doesn't matter what the person did. They put the part in there and it puts it in the right location. Don't let the person be the thing that limits it. Okay, precision you will hear used a lot. And precision is when something is both accurate and repeatable. You will hear people use precision in place of accuracy a lot. They do not mean the same thing, but you'll hear a lot of people talk about the precision of the process, and they only mean the accuracy of the process. It's like just the way it is. Right. So I want to know this. With somebody next to you at your table, or maybe two people, if you're at a 3-people table, how many length or distant measurements tools can you think of?
Calipers.
Ways to measure. So make a list.
Can we rewrite them down?
Sure, write them down.
Scale. Balance.
Write it down.
Length or distance?
Oh, balance is not. That's not. The phone measure.
Yeah, like a scanner.
I don't know if they make a better one. Hopefully they do. My phone sucks.
I like that.
visual
The
Okay.
Just write the list of things. They'll get what we need.
Construction and stuff that they had to
It's like a string that's a sentence. They do it every year.
That's just,
It's like a 10-yard string. Like a string.
Well, sonar
All right. Let's see what you thought of. How many did you get? Who has more than 15?
Oh God.
All right. Nice work. Okay, so let's see what we have. This table, what's one that you came up with?
The little wheel thing that you use to measure miles.
Okay, the little wheel thing that they use. All right. Yep, the little wheel. Good. Excellent. This table, or yeah, with two groups here, I guess.
We had,
We just went with calipers.
Calipers. Excellent.
we said sonar?
Sonar. All right. Good.
Hands of the horse.
Hands of the horse. Yes, hands are done this way, I think,
Okay.
because their hands are weird. There are 4 inches in a hand, which is the 4 fingers, I guess. And
Yeah.
so you can, yeah, hands of the horse.
That's
I guess that's how, I don't know, something like that. All right, was this one group, this table?
No,
Or-
it's two.
Okay, what,
Like that, the measuring tool that you use in construction, like the lasers and the eyeglass.
okay, yeah, so that's a transit or a theodolite or a total station, depending on what brand and how awesome it is. Okay, great.
I don't know, we said literally anything as long as it's cohesive. You know, as long as you have 3 Sharpies, you can use those to measure.
Okay, all right, so you can make something into a measuring device, good, yes? GPS, all right, great.
Pedo tube.
A pedo tube.
What is it? It's like it measures airspeed velocity.
Airspeed velocity is not.
Oh, right. But like, I don't know, it measures air pressure.
Sounds cool.
That's not it sounds.
Lasers.
Lasers. I'm not sure the pedo tube works. It's based on it, but anyway. Lasers. Lasers in the form of interferometers.
Oh, that's a good word.
And lasers in the form of laser tape, they call them laser tape measures, which they use the time delay. Yes?
Can I say this? I thought of the thing in football where they have the string and it's like a measured piece of string.
The chain.
To mark it down.
Yeah, the chain, right, good. Yeah, so the chain is a good one.
Can we just go with a ruler?
All right.
Oh yeah, the
Steel-
iPhone measuring app.
steel
It
ruler,
sucks.
iPhone measuring app, okay. Any more?
Oh, keep going around.
Knots in a boat, like.
Okay, yeah, so, a rope with knots tied in it at fathom measurements every 6 feet, right?
We have, oh yeah, radar.
Radar, okay.
You do, what's it, roads of chain? That's how you measure a chain, it goes down an anchor, how many roads of it.
Okay, yeah, so, chain lengths, okay. Any others?
Measuring tape.
Measuring tape, all right, good. They tried to steal your measuring tape by claiming any ruler, but I'm gonna allow that because it's a Rolly ruler.
A 5'8" person.
Sorry?
A 5'8" or 6 foot person.
Okay, all right, yeah, so a person's height, right? Because you often do that, right? You're like, you look at the person next to the building and you're like, yeah, that's about 12 feet tall.
Probably like 6
Sorry? A height gauge, yes, a height gauge. Boy, that's embarrassing that I did not have that on my list. I'm going to add that. I'm going to add that to my list so that I look more accomplished in my work.
Triple beam balance.
A triple beam balance. So that, does that do
Oh.
distance or length?
Oh, we're talking about like, distance. I'm thinking of something completely different. I'm just like, measurement tools.
All right.
I did not read the prompt.
That's good. Okay, we're just gonna stick to length and distance, or we'll be here all week.
Is there a thing, I was just curious, is there a thing that exists that's like a circle that like shrinks so you can measure how wide circles are? Like there's like a thing that like.
Oh, with the
Temperature or
iris?
something, or-
We go next, we go
Yeah.
next.
It's like a drawing tool, there's like graphic.
It's like a thing that measures the diameter of circles and you can like draw with your pencil in it.
Oh, yeah.
All right.
A compass? Is that what you're talking about?
No.
I mean, you got standards like gauge blocks and gauge pins and
Yeah.
radius gauges and
Radius
pans.
gauge.
Yeah, radius gauges. So you have just standard items. So I brought the gauge pens. There was a group in the lab quizzing me about what we were gonna do with the gauge pens. I just brought them, nothing else. By the way, they are typically not spelled this way. Ben put that on there. They're typically spelled G-A-G-E. You can spell them either way, but they're typically misspelled in metrology. So gauge pens, they just are pens, and they will say different diameters on them. They're generally good to at least 10,000ths of an inch, and sometimes better than that, depending on what you buy. And so you just take those and see if they will fit in the hole. And they are difficult to get in the hole if they're really close. What might be some, well, no, that's different. That's a next problem. Yes?
The little thing of like, in the old days of like walk along maps to measure distances.
Oh,
Oh, yes,
Yeah.
that's a divider, I
I got
think.
one.
Yes.
Coordinate math.
Coordinate
Yeah,
math.
like you get the coordinates and then you do the math of like how far they technically are.
Yeah, but you didn't measure the coordinates, so we have to
How,
go
well,
with
how do
what
people
got
measure
you.
coordinates?
GPS.
GPS and theodolites.
Dang it! Okay, that
Well,
second one.
and chains.
Yardstick?
The old way was to use chains along the ground.
Oh.
Any others?
The equator.
Yes.
That like gauge reader that they see in the hot metals labs, those like little ones that have like the certain gauge things around the outside. You know what I'm talking about?
The little gauge things around
It's like it's a metal circle and it has certain gauges cut out of it so you can measure.
Oh, you can just put
metal.
something in it to see if it's the right size? Okay, yeah.
Well, does the length of time count? Like a watch?
Length of time, no. Time is different. We're only doing distance. An astrolabe.
Whoa.
That gives you position. I guess if you
did it
take
twice, you
two
get this.
position measurements, you get distance.
And coordinates didn't count?
Well, you can use an astrolabe to determine your coordinate. Yeah.
I'm mad at you.
I was gonna say something else, but that maybe take like, does telescope count? Cause you can like measure distance, like.
If you know the
If you know how far
if you know the
it's like-
magnification of it, you can be like.
It only counts if you have something so you can measure the red shift of a planet, so you can tell, but that's
Well, you could,
actually
like, see the
velocity.
parallax or whatever, and like, if you get too.
But without the angle measurement of the astrolabe, it doesn't give it to you.
Okay, anyway, I was gonna say like the little rolling thing, like, for maps, like
Yeah.
kinda like the big construction one, but like the little version where it's just like.
Right, there's a little rolly thing that you can roll along the map, yes.
Like in baking or quilting, you just have a big mat that has
It has a-
certified circles or squares.
Certified.
I don't know.
Oh, like a macaroni.
Like that.
I know, yes, I agree with you. So we're gonna call that a gauge. We're gonna call that a gauge because it's sort of in the set of things where you create something that is a size and then you measure to it. Yes?
An odometer.
An odometer, yeah, okay, I guess an odometer is different than the little rolly thing because it's connected to your car. Sure. Yeah.
Just eyeballing it.
Just, yep, that's good enough. All right, so, this minus the one that I added at the end there is the list that I came up with. We didn't do, foot, arm span, or stride length, which are ways that people often measure things. But
I feel like person is.
otherwise, I think that we got everything on there, so good work. We don't have anything else to
You know,
learn.
sometimes I do that.
Well,
When
okay.
someone's like a building is 100 feet tall, I think of how many people.
Yeah, what is it?
What is a
If
total
they were stacked
station?
on top of each other, would be like.
A total station is a theodolite for measuring on a construction site. So the little thing that you peer through on the construction site and you can see something a ways away, but it has extra superpowers. So it has a laser to hit a reflector, so it will do a laser measurement of distance, and then it has internal sensors to sense all the angles. And so you can take the shot, you name that, and then it downloads all the data afterwards and will map it for you.
Superpower.
Yeah, it's got superpowers. Sweet.
Sweet.
All right. That is the wrong stream. That's why that is not going forward. It's now going to go forward. All right. How do we choose the other metrology tools that we want to use? So we talked about accuracy and repeatability, but there are a bunch of other things that we need to understand about a metrology tool to decide if it's the right one for a situation. So the first thing is that the best case, or the case that you should strive for, is that the gauge capability is 10 times better than the accuracy that you need to measure. Now, we rarely achieve this, but that should be our goal, that your measurement device is 10 times better than what you need to measure. So if you need to measure thousandths of an inch, it is best if your gauge can measure tenths or 10,000ths of an inch. All right. Now, what is sort of the minimum? The minimum would be about half. It absolutely has to measure half of your required accuracy. Otherwise, you really don't know where you are. Second thing is the range. You have to understand the range of your device. Does it measure 6 inches? Does it measure 6 feet? At NIST, we saw the coordinate measuring machine, and it can measure about 3 feet by about 4 feet for the measuring machine that we saw. NIST also has something called the M cubed, and it is in a sphere about this big, and its entire measurement range is less than the diameter of a hair. Its accuracy is phenomenal, but its entire measurement range is about the diameter of a hair. It's a huge machine, cost millions and millions of dollars to make. We need to understand the resolution. So on your calipers the other day, I said that you need to get calipers that say 0.001 because we need a thousandths of resolution. So that is the distance between marks. Now, we can argue, and we will argue a little bit about if that's the smallest that we can measure or not off that device. We need to understand the robustness of the device. How good is it in adverse conditions? So these gauge pens are often used on the shop floor. So you can take a set of these to the shop floor, and if you just made a hole in something, you can take these gauge pens and you keep trying gauge pens till you find out what the size is. They make gauge pens that are 10 times more accurate than this. When you have those gauge pens, they don't leave the metrology lab. And these, you go out to the shop floor and you just use them. But the ones that are made to 10 times more accuracy than this, you would never use without wearing gloves. You would always have gloves because the thickness of fingerprints and especially the rust that comes from some people's body oils will cause them to be inaccurate. We had a name for such people before, but I won't share it because it wasn't very nice. But anyway, some people, their skin oils are really acidic, and so it will rust things like that really quickly.
That was my question.
Yeah.
Why it happens to some people and not others?
I don't
Like,
know.
is it diet, do you think?
I don't have any idea. I'm going to blame it on genes because that seems easier. But I don't know the answer. The rate, how, I got an email. I feel so honored. How fast can you take the measurements? So in a couple of days, we're gonna go to the lab and we're gonna use micrometers. And we're also going to use the calipers. And one of the things that we're gonna find about the micrometers is that unless you're really good at them, even probably if you're really good at them, and if you can get them out of the box, they're just slow. It is slow to use them, it is slow to read them. You can get faster micrometers that are digital, but they're still slow to use in comparison. And so, yeah, some things are quick, some things are slow. The coordinate measuring machine that we saw the other day, we'll see a video of one running in not too long, slow. They take forever. They're super versatile. They're really, really good machines, but they're not fast. Repeatability. We need it to achieve the same measurements time after time after time, and we need to understand that so throughout the day it's receiving the same or making the same part, that kind of thing. I had a video that was part of the video series. I took it out and replaced it with the NIST video, but it was one of a company, I don't know if any of you have ever watched NYC CNC, but it's they're good videos, and he was talking in that video about the fact that they had this machine. It's not a super high quality machine. It's like the Haas machines that we have. And they were holding 10,000ths of an inch on that machine. And then they couldn't. And then they could. And then they couldn't. And they were trying to figure out what was going on. And what they figured out was partway through the day, somebody was getting too warm and opening the garage door a little bit on one end of the building. It wasn't anywhere close to the machine, but that temperature difference would throw off the machine. They also had things with it like they have special programs so that you can warm up the spindle of the machine, and what they had found was they had to warm it up within a certain amount of time of running these parts. And so they now have something in the code, so when you go to run your program, it checks to see if it's warm enough before it runs. So anyway, more, how do I choose metrology tool? Stability, so this is a lack of drift. This is primarily with electronic instruments. So electronic instruments tend to drift over time, and so if you take too long to take the measurement, it will not be accurate anymore. This happens especially with devices that measure force. So force measurement devices drift really badly. Yes?
Is that why when you're using like a scale, like the last digit just keeps jumping up and down?
Yeah, that's instability in the system and building shaking and all that. It would be interesting to try that on the two different ends of this building and see where it was worse. So you know this building, the front end is in a swamp. Western was put here because there was a swamp, right? There was nothing here. Whenever you come to a town and you say, I want to build something big, and there's a big open area, you should ask yourself, why is it a big open area? So anyway, there was a swamp here. They put a university in the middle of it, and this building is right on the edge of that swamp. So the north end of the building is in the swamp. The south end of the building is on rock. And you can see that on the second and third floors, there's a big plate across the floor in the hallway, and that's because it's where the building is cracking apart slowly and coming apart. You can also see it in the main, well, you used to be able to see it in the main office. On the doorway to the conference room, I can't remember if it's still there. Anyway, there used to be a big crack going up from the edge of the door, and they have two little markers on it so they can track how quickly we're sinking into the swamp. Anyway, it'd be fun to find out if it's better to be on squishy ground or on rock for that. Cool. Maybe we'll have to get a grant and do some study. Magnification. So there are lots of ways to magnify a measurement. So when you are using your calipers, even on the dial calipers, you're doing magnification, right? I make this little tiny movements of a little bit, a few thousandths of an inch, and this needle is swinging a long way around. So the magnification on here is twofold. There's a little gear in here that's riding along this rack on the bottom, And that is making, the gear ratio is making 1 magnification, and then just the length of this, this pointer. If it's had a big dial with a big long pointer on it, we would have even more magnification and we could see better resolution from it. Now, we might find out that if we did that, the gear was not high enough quality to support that amount of magnification. The more magnification we have, the more noisy it gets. So we would see the end of that needle oscillating back and forth, especially when we have electronics. The more magnification you have, the more noise you have in the signal, and the harder it is to tell the real signal from the fake signal. Surface cleanliness. How good is our system at measuring with surface cleanliness? On your calipers, there's a section that's flat, and there's a section that's sharp. The flat section is a lot easier to measure things with sometimes because it will sort of level out. It will sort of allow you to level out, and you can feel when it is measuring flat against the surface, which makes it measure perpendicular to the surface. But if I'm measuring something that might have goo and chips and little particles on it, and I measure on those flats, all I'm doing is guaranteeing that I'm going to be measuring on top of little goo and particles. But out here on the sharp part, if I measure with that, I'm more likely to either displace those little particles or to not hit them at all. And so on calipers, there's a section that has better ability to adapt to cleanliness issues. Or I could just clean the part. That would be a better approach overall. We have to choose contact versus non-contact. So calipers are contact. I'm contacting the surface. There are lots of laser measurement methods and other things, electronic measurement methods that are non-contact. There is a lot of certainty in contacting the part. When you don't contact the part, it can introduce all sorts of things into the system that are very hard to find. Like some of the ways that you measure surfaces, just an oil sheen on the surface will throw it off. And so you actually don't get the right answer because of a very thin oil sheen. Have to look at the budget. So calipers are really cheap. That's why we make them, why we make you buy them. Coordinate measuring machines are not. That's why we did not make you buy your own coordinate measuring machine to haul around the building. So that would be really cool. I mean, if everybody had one, you'd be the coolest kids on campus.
I don't think anyone else would think that.
If you were hauling around the little wagon with the CMM in it,
No one's gonna think I'm cool, Gil. I'm sorry.
Well, it's, you just don't have your own metrology.
okay.
The people in this building would think I'm pretty cool.
There could be some accusations of needing a life, but I mean, metrology is more important than being cool. And metrology is cool by its very nature, so it's good enough. All right, ease of use. When you folks use the coordinate measuring machines later this year, you will find that the coordinate measuring machines that we have are bonkers hard to use. They are so bad. Oh my goodness. And oddly enough, almost all coordinate measuring machines have the same terrible software, or they're about 4 different versions, but they're all terrible. And they just, it's not a big enough field for them to make it better, I guess. I don't know. Anyway, durability of the process. The calipers will last a long time. You can throw them in your backpack and life is good. A lot of the other metrology things that we have in the building, I would be very disheartened if you threw it in your backpack and carried it around. And number of measurements to be taken. That kind of goes with the rate at which we can take it. So what I would like you to do is I would like you to think about calipers, tape measure, just using a folded piece of paper. So somebody said highlighters. You said highlighters. You can measure something in highlighters or hands or feet or any of those things. So you can take, right, we know that a sheet of paper maybe is 8.5 by 11. So you can take that and fold it in half. You know that your 8.5 became 4 1/4, and you fold it in half again, and it now became 2 1/8, and you fold it in half again, and it's 1 1/16, and you fold it in half again, and it's a half plus a 32nd, and you keep going. So anyway, what I would like, and a ruler, so we'll call it a wooden ruler for this, just for the sake of discussion. So what I want you to do is rank for range, which of those has the best range, the biggest range, and which one has the worst range. So best gets a 1, 2, 3, 4. And resolution, and go through that set. Yes.
We're just thinking about the small calipers, not the.
We're
Not
gonna,
like-
yeah,
not
we're gonna
like-
go with the calipers that you
Okay.
purchased,
Because
not,
they don't have
there are big
different
calipers,
calipers.
yes. There are also,
Gigantic calipers.
there are also big sheets of paper.
This doesn't help.
Yeah, I was
Okay,
kinda
so
like.
tape measure. Please rank.
Yeah, then I would say folded paper ruler calipers. That could be pretty big. Like this size.
It's still bigger than a
Okay, what about a 12?
Yeah.
So technically the rule is
We're doing it more.
Okay, so caliper.
Okay, resolution. Smallest metric out calipers.
One is 8,
And I would say